Open SubMeshProject and set the units as displayed. To create the geometry, we select the planar tool to construct the shell geometry from the given IPE 100 section. Under the surface group, select planar. The flange of the I-beam lies in the XY plane and the width of the flange is 55 and the length 2000. The method in the open window is the one-point method. In the points text entry box, type in 0, 0, 0. This initializes the center of the flange at that coordinate. The plane we are working with is the XY plane. Under the dimensions, type in 2000 in the length text entry box. Press tab and type in 55 in the width text entry box. Select preview and determine if the orientation of the bottom flange is correct. Select apply. Now we create the top flange. In the point text entry box, type in 0, 0, 94.3. Select preview. Notice that the top flange is offset by 94.3 mm, which corresponds to the height of the web. Select apply. For the web, we initialize the center of the web halfway between the top and bottom flange. In the window that is still open, in the points text entry box, type in 0, 0, 47.15. Select preview. Notice the position of the web. The web of the I-beam lies in the XZ plane and the height of the web is 94.3 mm and the length 2000. Select XZ for plane and select preview. Notice the orientation of the web. Define the length as 94.3 and the width as 2000. Select preview. Notice that the web is orientated correctly. Press OK. We create a reference point now which will be used later on and will have no influence on the results whatsoever. In the construction geometry group, select the point drop down and select X, Y, Z. In the location text entry box, type in 0, -30, -30. Notice the asterisk. Select OK, select Save. Now that we have the geometry, we have to mesh the geometry. Select the Meshing tab. In the Auto Mesh group, select Surface. In the Surface to Mesh, select Box, select the 3 surfaces. In the element size text entry box, type in 25. Because the geometry is rectangle in profile, it does not matter if we select the quite dominant option for mesh type. For mesh method, leave the auto decide selection. Press enter. Because we created 3 different planes to represent the flanges and the web of the beam, we need to make sure it is analyzed as one part. Select the Nodes Elements tab. In the Modify group, select Equivalent. In the Merging Tolerance text entry box, type in 0.2. Select Preview. Notice that the nodes on the web intersecting the flanges are highlighted. Select OK. Now the 3 planes are merged into one beam represented by shell elements. We need to determine if the quality of the mesh is acceptable. The more quality criteria the element fails, the less accurate its results will be. Select the Quality tab. Within the Checks group, select the Check Quality tool. On the open window, select the 2D Elements tab. Select Apply and then select the results. Notice that there are no failing elements. For a more visual display of the elemental quality, select the Element Fringes tool. Deselect the Element Fringes tool, select Cancel to close the window, select Save. In order to solve for the stresses in elements, we need to assign a material to the elements and the thickness. We will focus on an isotropic material for this tutorial. Select the Materials and Properties tab. In the Materials group, select Isotropic. In the Name text entry box, type in Steel. Type in 207,000 in the Young's modulus text entry box. Since we have the unit set to millimeters and newtons, this corresponds to 207 gigapascal. Define the Poisson's ratio as 0.3. Press enter. For linear static analysis, we only need these 2 material properties to successfully solve for the stresses in the model. In the 2-dimensional properties group, select Shell. In the Name text entry box, type in Flange. In the Entity selection tool, select Surfaces. Select the top and bottom surfaces. For the material, select the drop down and select Steel. For the thickness, type in 5.7. Select Apply. In the Name text entry box, type in Web. In the Selection tool for entities, select Surfaces. Select the web. For the thickness, type in 4.1. Select OK. Select Element Detailed Drawing drop down and select 3D Shell Thickness. Deselect the Element Detailed Drawing and save. Loads and boundary conditions should accurately represent real-life loads and constraints, and is very important to get it right. Select the Loads and Boundary Conditions tab. In the Constraints group, select Fixed. In the Entity selection box, deselect Nodes and select the Curves. Select the 3 curves on the leftmost of the model, select OK. Select the Bottom View. Now we will use the reference point created earlier to help apply another boundary condition to the model. Zoom into your area of interest. In the Constraints group, select Pin. In the Entity selection box, select Nodes in the Selection tool. Select the nodes in line with the reference point on the bottom flange. Deselect TX for translations. This will ensure translation in the X direction. Select OK. In the Loads group, select Total Load. In the Entity selection box, select Curves in the Selection tool. Select the curve representing the top of the web. In the Total Load text entry box, type in 3000. For the direction, type in -1 in the Z text entry box. Select OK and then save. Let us run through the checklist to determine if we covered all the aspects of setting up the model before we submit the problem to the solver. We got the geometry. We messed the geometry and checked the quality. We created the material and assigned the material with a thickness. We constrained and loaded the model. Now we can create a Nastran job which will be submitted to the solver. Right-click on a file set under the Model Browser pane. Select Create New Nastran Job. For the job name, type in Beam 2-dimensional. The solution type should remain Sol 101. Under Solver Input File, select the folder where you saved the model. Select the Save button. Select OK. Under Simulations, under this file set, right-click on the Nastran job we name Beam 2D. Select Run. Check the FO6 file to make sure the solver is done. To do this, we search the file for Fatal. If the search for Fatal returns no results, the job was solved successfully. Any fatal errors that are returned in the search for fatal should be rectified before the solver is run again. Now we can attach the results. Select File and then select Attach Results. Make sure the file to be attached is the Nastran job name with the XDB suffix. Select OK. Under Results tab, select Deformation. Select Update. Select Fringe from the Type drop-down. Select Stress Tensor and then von Mises select Update. This illustrates the stress distribution through the model and the deformation experienced by the model. This tutorial was brought to you by STEC.